Okay, all right, so I think we can get started. So today will be the last crash course for deep learning. So basically we'll talk about attention mechanism and also the transformer architecture and how the transformer architecture can be used in computer vision applications, okay? So for the attention mechanism, so basically by the name, right, by the term, so it's used to selectively focus on most important parts of the input, right? So maybe like if you have an image or a sentence, right, so not all of the input parts will be very useful. Then if you spend a lot of, computation on those maybe not relevant or important region, then it's not going to be very useful for the final prediction, right? So we want to focus on our computation, right, on the most important part, right? So that's the like the basic objective for the attention mechanism. So it will allow a network to dynamically weigh the importance of different element, right? So we want to maybe assign a higher weight to like pixels or the tokens, right? If we're doing the sequence modeling that are most important, we want to have a higher weights on that. But less important ones, we can assign a smaller weights, right? So we don't make, take too much of those information into account. And so these attention mechanism has been proved very useful in tasks like machine translation, image caption, and also models have to consider different parts when making prediction, right? So like the machine translation, some of the words doesn't make useful information, right? So we don't have to pay attention to that, and also of course image as well, right? So a lot of regions that maybe does not convey very useful representations, then maybe we don't have to spend a lot of computation on those regions. Okay, so that's kind of like high level, right? Why do we want to using or develop this attention mechanism, and how it is able to help with some of the learning tasks. So last lecture we've talked about recurrent neural network, right? So let's see how the recurrent neural network can be used with these attention mechanism, or how we can build or incorporate this attention mechanism, right, in the RNN structure. Okay. So let's look at the bottom, right? So here, this shows a bidirectional RNN, right? So the bidirectional means I have a forward pass, right? So here is the hidden activation, right? H, F indicating this is a forward pass, right? B indicating this is a backward pass, right? So this is become a bidirectional. So we have this input, right? So let's say this is different words or token embeddings. So then we have this hidden activation HF and the HB, right? So then we also have get these hidden activation here. If we don't using any of the attention mechanism, right? So then we'll go to this like a decoder RNN here and trying to make a prediction output, right? So the Y1 maybe you're doing some translation. But if we're using the attention mechanism, as you can see here, right, so we have these A or alpha, right, so these are the attention weights, alpha 1, 1, alpha 1, 2. So if we look at the first input, right, X1, so these are kind of like our attention weights, right, so how much I have to attend to for the rest of the input, right, or the tokens in the original input. So these are alpha 1, to alpha 1 t minus 1, these are the attention weights, okay? So then basically we can, using these attention weights, right, to weigh these hidden activations, right, we can multiply this with H1, alpha 1, 2, multiply with H2, right? So eventually we'll get another kind of like a weighted activation as C1, right? So this is basically incorporating some of the context, right, weighted context information, right? So we kind of look at the entire sequence. So bring some of the context notion, right, and also these weights will assign, right, different weights for different the input activation. And you may wondering, right, how do we come up with attention weights, right? So it can be learned by like a neural network, right? So we may come up with some simple MLP layer, right? So we can using this to predict these attention weights, and eventually, we can also want to using the softmax, right, to normalize them to between 0 and 1, and they all sum to 1, right? So we want to have these attention weights to have some of the meaning, right? So a larger weights means a higher probability, we want to pay more attention to this maybe particular hidden activation, okay? And so this is like a visualize these attention weights, right? So like, so I think this is maybe translate from English to French. I don't know if you guys, maybe this is French or maybe other languages. So you can see that, right? So some of the words, so the diagonal, right? So it's like the attention to itself. But there's also some of the words maybe not just pay attention to itself, but also some other words, right? So they maybe have some close correlation. So if you look at, let's maybe see, if you look at this particular number, right, 1992, so I think this is some of the dates, right? So like intuitively then, this maybe like you can consider like this is like a standalone concept, right? Maybe not have much correlation to other words, right? Like the sign or words, right? Doesn't seems like there's too much correlation between these number. So if we look at this, right? So the attention here, right? So basically it's just pay most of the attention to itself, right? Not attend too much of the other words, right? But this is just a very simple example to show, right? So how these attention weights will be eventually reflected, okay? And we also have attentions in CNs, right? So here, just make an example, this squeeze and excitation network. So this is also using the attention mechanism, trying to weight different feature channels, okay? So in this very simple diagram, right, so they have, like this is the conv layer, right? So we have this feature map, H and W indicating the height and width, and also you have the number of channels, right? And what you would do here, right, so you basically have normally, right, so if you, this is their incorporated module, right? So they call this squeeze and excitation module. So if you don't have that, this is just like the standard or conventional CNN, right? So you have these conv layers. And their squeeze and excitation module means here you want to compress, right? So you have this global average pooling, right? So which means for each of these channels, right? So one channel, maybe here, there's going to be another channel like this. You basically do the global average pooling, right? So you end up with 1 by 1 by C, right? So you have C numbers, right? So each channel will collapse into a single scalar, right? Using like global pooling. And then you can, add in some of the learnable weights, right? To maybe some MLP to learn these weights. And eventually then you can multiply these, the learned weights, right? Multiply that. This is a scalar to each of the channel, right? So trying to, so these are like the channel weighting, right? So how much, maybe this channel is really important, learning some representation, very useful, but some of the feature maps maybe it doesn't, extract very useful information, right? Then we don't have to rely so much, right, on some of the channels. So that's the channel weighting they are introduced in this network, okay? And see, here they were able to incorporate the squeeze and excitation idea or module with different existing CN architecture, right? So we have this kind of inception network, right? So they have the inception module, then you can incorporate these squeeze excitation idea, right? So you do these global average pooling, a couple of fully connected layer value, right? So trying to come up or learn how you should weigh these different channels, right? Then eventually you multiply with that with all the original feature map to do the weighting. Similarly, you can also do this in the ResNet, right? The residual connection with the residual connection. Again, so these are their part, right? So learn these channel weighting, and then you multiply with the original feature map, okay? Okay, so that's the very simple attention mechanism, right? So of course, this becomes like the main backbone, right? So when we talk about the transformer architecture, which is used a lot in not just in NLP, but also vision and multimodal modeling. So next, we're gonna dive deeper into this transformer architecture and see, especially learn this kind of self-attention mechanism, okay? So this transformer, so this is the paper, right? So attention is all you need, right? So they introduced these self-attention mechanism, and it's got a lot of citations. So this number needs to be updated. So I think this is from last year lecture. So they may get more citations. I think, yeah. So I think this may be more. This is published in 2017 Europe's, right? So, and coming from researchers from Google Research, Google Brain, and also University of Toronto. And since this invention of the transformer architecture, right, so it becomes the default, like the backbone architecture for a lot of large language models, right? So here, so we will see the network gets deeper, right? The number of parameters get more and more, right? So like in the CNN, we have like millions of parameters, but now, with these large language models, with the transformer architecture, right, we have like billions of parameters, right? So, and this curve is keep kind of scaling up, right? The scaling up of the model. So the assumption is that if you can, if there's a scaling law exists, right, you can scaling up the number of parameters and the compute, so you get more performance gain. So basically the transformer architecture is that, try to get rid of all these, sequential parts, right? So we don't have this, recurrency, that is in the recurrent neural network, and then there's no convolution, and it will solely rely on the self-attention mechanism, right, to process the whole sequences at once. Okay. So before I, talk, or maybe we look into the self-attention mechanism that is in transformer, just want to briefly talk the basic form of the self-attention. So you get just to ease the understanding, right, later how these self-attention mechanism was used in the transformer architecture, right? So basically, we will look at how we can derive the very simple or the basic attention weights, right? The similarity between current input and other inputs, and how we can normalize weights, and how we can compute the attention values, right, after we normalize the weights. Okay. So basically, at the high level, right? So you basically look at the equation like this. You have different. So you want to compute attention weighted output, right? So maybe for the ith input, then you will need to compute all these weights, and you are using these weights to multiply, all these other tokens, right? So how much you want to attend to, right? Respect of the rest of the tokens or input. And so the attention weights, can be computed using the simple dot product, right? So here, by the way, like why we can using the dot product to capture the relationship, right? So you can view the attention weights as sort of a relationship, right? Or the similarity, right? So why this dot product is able to capture that? Anyone?
Well, so every token gets to talk to the other tokens, and vice versa. So, right?
So yeah. So is the dot product give you some sort of relationship or similarity? What does that indicate?
Well, if you multiply with itself, it'll be like what we saw earlier.
Mm-hmm. So if you kind of, for this dot product, right? So like, I think I have some. Yeah, maybe I can write here again, right? So you have a. Maybe we can just use this one. It's really hard to write. I don't have a stylus. So this one, you can extend like xi the magnitude, right? So if you look at the dot product, so you have the magnitude multiply with xij, the magnitude of another vector, right? So this is in the vector form. And what else we have if we kind of extend? So the magnitude, we also have a cosine theta, right? So theta is basically the angle between these two vectors, right? So this is kind of similar to a cosine similarity, right? So basically, if these two vectors align with the same direction, right? So the theta will be very small, right? So this means that they are very close in the high dimensional space, right? If it's perpendicular, you will get a 0, right? If it's opposite direction, right, so you get a negative number, right? So, and usually, dot product, considering the magnitude of these two vectors, but if you only considering the cosine similarity, basically it's just normalized, right? You basically consider how close these two vectors, right, in their high dimensional space, considering these angles, right? So this is some sort of like a similarity measure, right? So how close is these two different, vectors, okay? And of course, then we can using the softmax, right, to scale them, between 0 and 1, and also sum them together should be equal to 1, okay? Oh, okay, yeah, I write it here, right? So this is the form for the dot product, okay? So let's look at just using this drawing to give you a very concrete example, right? So the very basic form of this self-attention, right? So let's consider we have an input sequence, right? So we have like T words or T tokens, right? So this is the first words or first token, right? So we have some sort of feature embedding, right? Like the word embedding. So this can be a high dimensional vector. And we have T of them, right? And let's look at the first one, right? So xi, individual token or word. So if we look at the x1, right, the first one, and we want to compute the dot product between x1 and the rest of the other tokens, right? So you have this, if we look at x1 here, then you have x1 times x1 itself, right? And x1, x2, x1, s3 to x1 to xt, right? So here you get a scalar, right? Because you're doing the dot product with these two vectors, you get the scalar ai1 to ait, okay? So that's the basically the weights. Of course, you want to apply a softmax to scale it, and then you basically multiply that with the original, right? So you ai1 multiply with xi, ai2 multiply with x2, right? So you get like attention weighted output, right? So this vector. So actually, this will taking into account all these input sequence, right? Because we are weighting them, and all these input vectors has been considered, right? So it has some sort of a context awareness, okay? But you may notice, right? So in this case, there's no learning, right? So basically, these weights is depending on whatever the input you have the embedding, then the dot product, that's it, right? So that's the weight. There's no learning involved, but this is the very simple and basic form of this self-attention mechanism, just to get you like started with what's going on. But then let's move on to this transformer paper, right? See how exactly they are involving some of the learning component so that we're able to dynamically optimize, right? What kind of weights, what kind of attention we want to assign to different tokens, right? So how can we?
Yes, like they are x1 to xt. These are the input sequence and the feature vectors of a single example?
So this can be like a word, right? So this is your word embedding, right? So you have a sentence, you have different words. So this will be like embedding, right? So this is another feature embedding. Then you basically compute this dot product, right? To get.
For the text input, but if it is kind of image, how?
Yeah. So images, right? So this can be like a patch, right? So the patch is, you can using some simple, CN convolutional layers to extract some features, and you have a feature embedding, right? Or if you don't using CN, you can using some of the classic feature extractor, any of the feature embedding, right? Edge detection or whatever, Fourier transform, wavelet transform, right? So basically just a feature representation, then you can compute, follow this step, right? Compute the dot product, get the similarity relationship, and get the scalar as the weights for the attention, okay? But again, there's no learning, right? So you basically compute that's fixed. Okay, so So for the self-attention mechanism in the transformer, right? So now what they do is they introduce 3 trainable weight matrices that is going to multiply with the input sequence or the sequence embeddings, right? So we have, they name this as query, key, and a value, right? So you have these query matrix, WQ, you have the key matrix, projection matrix, WK, and it has a value projection matrix, WV. You may be wondering, right, why are you using this, query key value naming for these 3 terms, right? So this, I think the analogy comes from like information retrieval, right? So in the transformer, so the query vector corresponding to the feature representations of the current token that is asking, right, how much it should attend to other tokens in the input sequence. And the key vector represents the feature of a token in the sequence. So it is used in conjunction with the query matrix. So we will see that later. So and also the value vector represents, right, the actual feature content of the token, right? So basically applying these attention weights. So this is the basically multiply with the value vector or matrix. They will result in an output. Okay. So this is basically we have like the previous example, right? So we have this t input, right? So x1 to xt. So now before we don't have these like weight projection, right? So we basically just using these feature representation and compute the dot product, right? But now we have these so-called trainable weight matrices, right? So we first multiply with these weights. So basically these weights project the input into kind of 3 different subspace, right? So one is with the WQ, the second is with WK, and the third is these WV, okay? So you end up with 3 different vectors, okay? So one is Q1, K1, and a V1, right? So for the second input, you have Q2, K2, and a V2, okay? Now, so for each of these input, right, so we basically generate like 3 different vectors, okay? Now, the next step is we want to compute the dot product. So let's look at maybe x2, okay? So I highlight with this box right here, right? Let's see, this is our current position or input, right? So this is our query. So here we are using Q2 as our query. Then how do we compute the similarity, right? So we are using the Q2, with the dot product with K1, and here we Q2 with a dot product with K2, etc. Okay, so in this case, we'll also get a scalar, right? A21, A22, right? This one the first index stay the same because we are using the second input as the query, right? So the second index indicating, with different or the other, tokens embeddings, okay? And once we have these kind of attention weights, right? So then we can multiply with the value vector, right? So A21 will be multiplied with V1, and A22 will be multiplied with V2, okay? So then you basically sum all these weighted vector together, you get an output, okay? So, of course, we will also apply the softmax to weigh, to normalize these attention weights. But in general, so this is the kind of, like you can consider this is a learnable version of the self-attention mechanism we just discussed, okay? Any question here?
For next is you interpret based on Q1, something like this.
Can you repeat your question?
Now it is showing based on the query parameter Q2, right?
Yes.
So each time you will calculate for the Q1, Q2, Q3.
Yeah, of course, you will compute all of them, right? So you start with X1. If you if we, let's say, you compute x2, right, next is x3, you basically take, the query becomes Q3, right? And then you will have Q3 here is K1, Q3, K2, Q3 to KT, right? So you basically using that to get the attention scores, and you multiply, then you're using that to multiply with these value vector, okay? Yes?
So the sum happens, so all the A matrices, they get summed together, is that it?
So this is just a single, right? So A2 indicating this is the like attention weighted output, right? So now you are no longer X2, you become A2. So A2 is just, so I probably should, so you have A21, if we again consider X2 as the query, right? So you have A21 multiplied with V1, right? And you here has A22. You have V2, right? So this is a vector, this is a vector, right? So I think there's a line right here, right? So basically you have this, you get this, and you basically sum them together, right? So this is the, like the weighted.
So it would be any scalar value at the end.
So no, this is a vector, right? A21, this is a scalar, right? You multiply with this V1 vector, okay? And this is A22 dot product, have a scalar, and you multiply with V2, right? You have a vector. So I'm not sure if there's any confusion. Just like this, right? So we have A11, so we will multiply with X1, we multiply this with X2, we sum them together to get a weighted output vector, right? So here is the same. Okay, so you have a output vector. Okay, we'll have more examples to help you to have a better understanding. Okay, so but this is just to give you a kind of detailed illustration, right? So how the self-attention mechanism is working under the hood. Okay. And so one thing we didn't talk about is the dimension, right? So in the original their paper, right? So here this each input token, right? So this is basically a feature embedding, right? So you have a dimensionality of DE, right? So we using like an embedding, right? Indicating embedding. So in the original transformer paper, it's 512. Feature representation, dimensional feature representation. And your weight matrix here, right, because you X multiply with WQ or this WK, right, you have these distinctive dimensions here, right? So DE multiply with DQ, that's the dimension of WQ, right? So in this case, you can multiply with 1 times DE. So that's the xi, right? So that in that case, your dimension of this matrix will match, right? So you end up with Q1 will be 1 times dq, right? So that's the vector of Q. Okay. So you will also have a dimension for this K matrix, right? You also have the dimension for this value matrix. Okay. So in their paper, just to simplify, so these, dq, dk, and dv, they all set, the same. Okay. We'll look at some concrete numbers. Okay. So, but this is just to make sure you have specify these specific dimensions that all these matrix multiplications is able to, operate properly, right? So there's no dimension mismatch. Okay. And of course, you can compute because not like the recurrent neural network, right? So you have to compute the memory, or the LSTMM, right? You have to compute the memory and then using that as the additional input to the next input token. But here we can run everything in parallel, right? So we don't have to wait for the self-computation and using that as the additional input. So we can actually, compute all these for different tokens, right, simultaneously, right? X1, X2, we can compute these like attention-weighted output, right? A1, A2 to AT, right? So you get this attention output. And here I'm just trying to make things more complicated, right? So before we are just taking a single this a token, right? So but eventually we can consider all these T embeddings or token embeddings, right? So we can write that in essentially the matrix form. Okay. Yes.
Go back to slides.
One slide. This one.
Not the previous one. So, like 821 is a scalar, right?
Which one? This one? Yeah, this is a scalar. Yeah.
So then 821 gets added with 822?
A21 multiply with V1.
V1.
Right, so this is the attention, right? So like how much I have to attend to these K1, right? So yeah, I know this is a little bit tricky to understand because you make these 3 copies, right? Before we just have only this one, right? So you can multiply with this X1, X2, get a score, right? So you weight that. But here, essentially, we are trying to have separate representations, right? So you can consider this V1 is the information I contain in the X1, okay? So some of the information I want to share with you, okay? But this weighting is basically trying to, okay, how much, I have to weigh this information.
Yes. So A21 gets multiplied with V1.
Yes.
V1 is a vector.
V1 is a vector, right? You scalar multiply with a vector, you still get a vector, right?
So the sum is vector-wise?
So so you have a vector, basically alpha 2, 1 multiplied with V1, then you have this A22 multiplied with V2, you have another vector, right? So they have the same dimension, right? So you can add them together.
Yeah. Okay, yeah.
Right?
Yeah, but A21 is dimension 1, right? So it's just a scalar.
Yeah. So this is dv dimension, right? So 1 times dv, right?
Okay, yeah.
So then you end up with 1 times
So A2 will also end up with the dv dimension, right?
yeah, the dk and the dv are the same, right? Dk and the dv are the same. So, but that doesn't matter, right? Because here you have a scalar. You have a scalar multiply with that. V1, V2, they all have the same dimension, right?
Yeah. So just to clarify, so
Mhm.
A2 is a vector.
A22.
Sorry, the A2, that one, the one.
This is a vector.
The one in blue, right below.
Yeah, this is a
That's
vector.
a vector.
So maybe this is kind of confusing, like a matrix form. Yeah. So this is actually a vector. Yes.
The diagram seems like A2 kind of like summing up something.
Yeah.
That's why
Yeah. So but here the diagram just shows you, right, how this A2 come from, right? So you weighting this vector V1 and using this scalar to weight that, and you summing them together, right? And you can see how the information coming aggregated from different tokens, right? So because these contain information from the second token input, the input, right? So this coming from the last, token or input, right? Yeah. Okay. But I think I have some summary or later like a graph illustration can make this more carefully. I will, summarize that. So if you are still not clear, that's fine. We will repeat a couple of times. Okay. So one thing I also want to mention is in their, the soft matrix, softmax. So this is basically this is the attention weight matrices. Okay, so you have these query times these the key matrix, right? So and you have these kind of square root of the decay, right? Trying to normalize that. So the reason they are using this kind of scalar to normalize is because, the softmax, right? So if we write out the softmax, right? So you have EX, right? So, and you basically sum all the EX, right? So if you have a large value, then you may end up with the gradient will become very small. So this is not very helpful during the training process, right? So you want to, for some numerical stability, right? So you want to do some scaling to help to preventing if there's such large numbers, then the gradient become very small. That's not very helpful for the learning process. And there's also in this figure, right? So basically, this shows you the process, the QKV, the scale, then it's the softmax, right? You multiply with that, get the scale dot product attention. And there's also one step, which is right here, which is called the mask, optional mask operation. So this is used to say you have in a batch, maybe you have different lengths of the sequence, right? So maybe some all have 3 tokens, but some maybe have 5 or 6, right? So basically, you have to see what's the maximum length in the batch, right? So if there's some sequence smaller than that, you will do some padding, right? So you have maybe a special, tokens, padding tokens for that. But those paddings doesn't have necessarily contain any useful information, right? So basically, then how do we try to or know the network to ignore those padding information, right? So basically, you can, using a masking, right? So if this is a padding, then you can assign maybe. So I think if you're using a softmax, you will assign minus, infinity, right? So you're using the minus infinity, negative infinity, and if it's the tokens in the sequence, you can using a mask value of 1, right, to indicating this is the actual token. But you're using this to indicating this is actually being padded just for the sake of the same length. So when you do the scaling, the softmax, right, it will become a 0, right? So in that case, we are not considering that padding token. Okay, so that's this mask is being used in this process. Okay, so here I give you some summary, what's the purpose of these 3 learnable projection matrix, right? So the input embedding in the sequence are often high dimensional, right? In the raw encoded raw information, but for the attention mechanism to capture meaningful relationships, these embeddings are project into these 3 different subspace, right? We call this query, key, and value, right? They have specific roles. So for these query projection matrix, right? So it determines how much attention a token will query or ask for other, tokens, right? So how much I should pay attention to you, right? So that's the query, and the key projection matrix, right, determines how the token contribute to the relevance of calculation, right, with respect to the query. Okay, and finally, this value projection matrix, right, so determines what information a token provides when it's actually attended to. Okay, so basically these give you 3 different representations. Another, maybe the purpose objective of these projection matrix is some sort of reduce the computation, because in their original paper, transformer paper, later I'll mention, because of using the multi-head attention, the projection matrix, you can reduce the vector. Let's go back to maybe this one. So let's say the original dimension is 512, right? So I can, using a projection matrix, to reduce the dimension maybe to 86, 64. Okay, so I think if they're using 8 multi-head attention, so they divided by 8, so this can be reduced to 64 dimension, right? So because these wave matrix, right, d times dq, d is equal to the input dimension, but the dq you can specify, right? So you can make it reduce to much lower dimension, right, from 512 to 64, right? So in this case, later when you do this computation, right, matrix multiplication, dot product, you don't have to involve so much computation. Of course, you can using the original dimension, right? You can keep it as the same like 512, but you can imagine, right, with all these matrix multiplication, how much computation is going to be. And of course, if you saw some heavy network, this embedding may not be just 512. They can be like 1,000 dimension or even more. So in a way, these projection matrices also serve the purpose of reduce or kind of balance the computation. Okay. So these different matrices, right? Because later we will basically optimize or learn these weight matrix, right? So they have a different kind of learning roles, right? So and they having them to separate will enhance the model to encode some nuanced relationship between different tokens. Okay. Okay, so that's the self-attention, right? So, but in the original paper, they are not just using a single set of these QKV projection matrix. They are actually using multiple attention heads, right? So they call this multi-headed attention, right? So they're using 8, right? So basically you have 8 sets of these, 3 projection matrix, right? So you have W1Q, W1K, W1V to W8Q, W8K, and the W8V, right? So these are separately learned, right? So this is one group or one set. This is another set. Their weights are totally different, okay? So the intuition for this multi-head attention is, you're trying to capture different types of relationship, right? So a single head attention may focus on a limited set of features or relationships because it's only compute a single attention, but maybe another attention head, right, trying to capture another type of a relationship, right? So then in this case, if you aggregate them together, you are looking at these kind of multiple types of relationships. So that maybe some of the tasks like translation or image captioning, understanding is able to learn better. And also they can help you to learn very diverse representation, right? Because different head may attend to different features or patterns, right? So that will lead into richer and more nuanced representation. And also, with multi-head attention, sometimes you can also mitigate the information loss, right? Because for a single head, you are compressing all information into one set of attention, but due to the heavy compression, then maybe some of the information will be lost, right? So if you are using multiple heads, then hopefully, other information can be captured from other heads, okay? And with that, right, definitely will, improving the, expressiveness, right? Because we are capture, different nuance these representations that can help enhance the representative or representation power of the network. Okay, so this is the figure illustrating the multi-head attention, right? So basically, if you look at here, right, so you have so these dimension here, they have some shaded here, so you have multiple head, right? So in their paper, they have 8 heads. So you generate these. For each of them, you have the scale dot product attention, right? You have output, and then you basically concatenate them together. Okay, so you're using the concat, right? So you concat all these like different heads. Okay, and finally, once you concatenate them together, you will have another projection matrix, WO here. So this is basically just do some linear transformation to make the dimension, the same as your input dimension. So this is not really very important, but the multi-head attention is basically capture different representations and you concat them together. Okay. Yes.
So in a transformer with many layers, it sort of expands and squeezes as it goes through the transformer.
Well, they don't have like the ResNet to squeeze the dimension, I think. But I think for some of the layers, they do have expand the number, the token embeddings. Yeah.
What I mean is, I think you said earlier that at the beginning, the projection matrix, it expands the input vector, and then at the output here, it reduces it.
Yeah.
So that happens every single time.
Well,
does it only happen at the beginning and at the end?
So the projection matrix here, the original embedding is 512, right? So the projection matrix, they end up with like a 64 dimension. Is because they are using 8 heads, right? So you concatenate them together. If you have 64, you have 8 of them, you end up with a dimension of 512, right? So that kind of preserve the original dimension. And so that in this way, when you're using each of the head, they will reduce the computation, but at the end, your information will not be lost because you highly compress them from 512 to 64. But you're using multiple heads, trying to kind of bring back those information. Is that your question?
Yes. So if like V, K, and Q, they go from 512 to 64.
Yeah.
And then the whole thing happens, and then concatenation brings it back to 512.
Yeah.
And then the linear, is that 512 to 512?
So I think in this case, this is depending on how you specify this H. So H is like how many, heads you have, right? So and also how you determine within a single head what is the dimension you have. So in their case, they happen to just uniformly divide the original input dimension with number of heads, but here you eventually, when you concatenate them together, you still result in a 512. But let's just say you are not using, 64. You're using 10, okay? So you have like 10 dimensions within each head, right? When you also do the concatenation, if you're using 8 of them, right, you resulting like 80 dimension, right? Then in this case, if you want to, because you're gonna stack multiple of these layers together, right? So you have another multi-head self-attention, then you want to go with the original dimension again, right? So then in this case, you can using this projection matrix, mainly from the 80 dimension project back to the 512 dimension.
Okay, yeah. I understand that. So I guess my question was, in practice, does it get like expanded or squeezed, or is it 512 to 512?
Well, it's up to your design, right? You can squeeze it, you can expand it, right? So you can specify those dimensions. Yeah.
Okay.
Yeah.
Makes sense.
Okay. Yeah. So this is like I said, right? So in their case, they have the original dimension is 512, right? Because they have using H heads, right? So for simplicity, they just divide the dimension, with the number of heads they use, right? So they're using 8 of them, so you have the 64 dimension. Then when you concatenate them together, and you eventually resulting like the same dimension as your original input dimension. Okay. Okay. So here, just like using like this kind of figure to summarize all these different steps, right? So you basically have all these steps in their original scale, the dot product attention, and this is the input, right? So you have like two word embeddings, right? So each row indicating a word embedding. Then you have these projection matrix, right? 3 of them, and you projecting the original input into like 3 different subspace, indicating with Q, K, and V with different rows we discussed. And then you are using the query and the key matrix, right, to compute the attention score, right? Then you will scale them to prevent a large value or later result in a small gradient. Okay, then based on that, you will multiply with these attention scores or weight matrices with the value matrix, right, to end up with the output matrix, okay, or the output vector if you look at individually, okay. And of course, you can using multiple heads, right? So this is one set of attention head, right? So this is another one. So here we show 3 of them, but of course you can make more than 3, 8, or even beyond 8. Then you basically concatenate all these output from these separate attention heads, and you using this weight matrix to project back to the similar input dimension. Then you go with another self-attention block. Okay, so you can repeat the process. Okay, so now I'm gonna do this one more time. Just give you like a step-by-step walkthrough. Okay, with their original dimension in the paper. Okay, so this is basically just to walk you through. Okay, so what's the entire process? Okay, so we have a input sequence, right, with n tokens, right? So n can be like the number of words in a sentence. So let's consider, here I'm using different notations, right? So I should be using the same, but just, here, this D model, which means like the word embedding. So just like before the DE, right? So the E indicating the embedding, okay? So we have the word embedding 512. So then we're using this X matrix to indicating this input sequence, right? So we have N, these words embeddings, each has these D model dimension. Okay. Okay, so the first step is we do this linear projection, right? Computing this query, key, and values. Okay, these 3 matrices, right? So each has these dimension specified, right? So they all has D model times DQ, D model times DK, D model times DV. Can you guys see this number? Okay. Okay, so for simplicity, right, so they define all these dk, dq, dv, the same, okay? And it will have a smaller subspace as compared to the original 512 input dimension, okay? So if we do this matrix multiplication, right, project the original input into these 3 different subspace will result in these 3 different matrices, okay, Q, K, and V. And now each of them has the dimension of n times dk, okay? It doesn't matter, right? Because dk, dq, dv, they're all the same, okay? So n times dk now. Any questions? So everything is clear, right? Okay. All right, so that's good. Then the next step is we compute this scaled dot product attention, right? So scaled means we have some scaling right here, right? So this is the dot product, right, if you consider each individual vector in this weight matrices. And so we compute, basically this is your attention weight matrix, okay, A. And for this weight matrix, right, so we have a dimension of n times n, right? So because Q is, we have, what's the dimension of Q? So n times dk, right? So, and the k transpose, which is, dk by n. So we end up with an n by n matrix of A. So each row, right, each row of this A matrix is going to be attention score, right, for the ith token, right? How much you have to attend to for the rest of the tokens, okay? And we have some scaling, right, to kind of, produce value from dominate the softmax. And the next step is we're using the softmax, right, to scale that to 0 and 1. And finally, we can compute this with the value matrix, and we get this output. Okay, so output will have the dimension of n times dv. Okay. So these output will basically kind of contextualize, right, based on attention, right, because it kind of aggregate or taking all these different tokens in the sequence into account. And we will also do this kind of multi-head attention, right? So we can have many different attention heads. So if we're using 8 of them, right? So we eventually will concatenate them together, and we resulting 8 times dk, right? If dk is 64, we resulting the n times 512 output dimension. Okay. And finally, we can using this WO matrix, right, to project back to the model size, right? So here, the model size, D model is also 512. And so that's the attention, but we can also adding some of the, like these classic layers, right? The feed-forward network, and also adding the residual connection, right? So which is help the gradient flow through the network if you have multiple attention blocks. And also using the layer normalization in the self-attention mechanism. Okay. Okay, so I hope this is clear to you. So I know some of the, these 3 different projection matrices can be confusing, but hopefully the summary of all these steps can give you like a clear picture, right? How these attention was computed at each step. Okay. So now let's look at, visualize these attention matrix, right? So what exactly, may look like, and how each of these attention value tell us, right? So here, I just make a very simple, or you call this like a dummy example. We have a sentence called the cat sat on the mat, okay, or sat on the mattress, and we want to compute the self-attention. Okay, so this is the self-attention matrix. Okay, so if we look at the first word, right? So this is the first word. Let's consider this is the query. Okay, and this is the the cat sat on the mat, right? So all the 6 words in the sentence, right? So we can see how much attention this one is attend to for all the words in the sentence. Okay. So if I maybe go to the next example slide. So if we look at the cat here, so for this example, right? So the high attention was, attend to the word set. Okay, so like the cat pays most attention to this verb, right? So. And if we look at the mat, right, so it's actually pay more attention to itself, right? It doesn't pay like too much attention to other words, right? So you can actually visualize these attention weights, right, to do some diagnosis, right? So if anything makes sense, right? So maybe this is not a very strong correlation or the example, but if you have some other sentences, right, maybe certain words, they have very strong relationship, right? Maybe this is the cause and this is the outcome, right? So you will see maybe the attention weights are very high because they are like a causal effect, right? So visualize this attention weight will able to help you, right? What exactly, if the network is actually learn something meaningful, right? So if the attention weights make sense, okay. Okay, so I think we talk about like the fundamental building blocks, right? These kind of multi-head attention in the transformer architecture. But because in their transformer paper, they are doing this kind of language translation, right? So the entire architecture actually consists of like the encoder, right? So left side, this is the encoder basically trying to encode the feature representations. then you also have a decoder, right, trying to decode, right, with the encoded feature in these kind of using multiple blocks of this self-attention blocks, right? How can we decode that into a different language, right? So you have this kind of decoder to kind of decode all these information. And another important aspect is the position embedding, right? Because if you don't consider the position encoding, it's we don't know, like if we shuffle the words, right? So they are basically the same, right? But for the sentence or for the image processing, right? So the position information is really important, right? Because for images, right? So how can we understand the layout, right? So this object is on the top, this object is on the bottom, right? So this one is to the left or to the right. So we need to have some sort of position information to encode that. So in their original paper, they're using this cosine, position encoding to assign like a unique positional, assign a vector to indicating a unique position, right? So that we know, if we change the order, right? So the position also changed. But of course, you can also using some learnable position embedding, right? Not just a hard code their position. You can also using a vector, let the network to learn, right? What are the best position encoding you can have, right? So it can also be a learnable position embedding, okay? So here also shows like attention weight, right? So the higher, the darker color means higher attention weights, right? So you can see, different attention heads, they do learn some, different attention weights, right? So maybe for the same sentence, right? So maybe this head learning something can be a little bit different than the other heads, okay? Okay, so I also recommend you have there's a very good YouTube video by what's the name? Three brown, one blue, I think. Yeah. So he's really good at making the animation, the math problem. So he has a very good video demonstration, right? How the internal mechanism works for this transformer. So I highly recommend you also, if you have some confusions, because the visual representation usually help your understanding, right? So if you are interested, you can see his video. I think is really very helpful. So you highly recommend you also watch that, okay? Finally, I also want to mention there's some limitations, right, for the self-attention mechanism, right? So if we notice or we talk about, right, so if the input, sequence is very long, right? So you have like thousands or even more than thousands of words, have very long sequence, or the embedding dimension is very high, then the computational complexity is kind of quadratic in the self-attention mechanism. Right, so this could be a potential problem, right, for the hardware, right, because you may not have a GPU that has very large memory, right, so train a large model can take days or even months, right, if you have a very large model. So people based on that has come up with some notable solutions or approaches, right, trying to reduce the complexity of the self-attention mechanism, right? So basically, how can we, reduce the complexity from quadratic maybe to linear, right? So there are some, notable solutions like the flash attention, right? So they are using memory-efficient attention computation to, reduce the memory complexity, right, from n squared to n times d. And there is some other approach, right, using sparse attention, like some of the attentions maybe, have the weights close to zero, right? Then maybe we don't have to compute for those attentions later, right? So we can using like a sparse pattern to do the computation to reduce the complexity. So here, just like a table to summarize, different methods, right? These flash attention, long former, their proposed method, what is their key features and what is their complexity as compared to the original self-attention. So the flash attention is actually being used a lot, especially in this modern generative AI, right? The GPT models, right? So, if you are interested, you can look at their paper and their GitHub. They have like flash attention 2. I think maybe now have flash attention 3. I think PyTorch also have some integrated flash attention operations there. Just to, if you want to using these efficient attention mechanism, you can call this flash attention. Okay. Other approach is not just focus on the software domain, right? So you can always think about how you can work with the hardware, right? So maybe you are not using the GPU, you are using some other hardware like FPGA. Then you want to, think about, because different hardwares, they have different specialties, right? So maybe you can cope with or work with hardware and do some co-design, right? To speed up the attention computation. Okay, so finally, I want to briefly talk about the vision transformer, right? So the transformer is first invented for the natural language processing, right? But later we also adopt these transformer architecture extensively in the vision community, and this animation just basically tells you, right? So how this vision transformer is being used. So basically, we are only using the transformer encoder, right? Because just like a CNN, we try to encode the feature representation. So the basic idea is that you can divide these images into small patches, right? Of course, you can treat images, each pixel as like a token, right? So then you can flatten an image into like a language or a sentence. But you can imagine, like, if you have like 512 by 512 image, if you consider each pixel as a token or input, you can imagine how long is that input is, right? So in this case, we want to reduce the computation. There, a clever way to do this is treating, instead of using a single pixel, I just, expand a little bit, right? Looking at a small region or patch at a time. Okay, so in this example, they are dividing the image into 9 small patches, right? Then each of the patches will go through some linear projection to get some feature embedding. Then the rest will be the same, right? So you adding up the position encoding, right? Because we need to know, what's the relationship between these spatial relationship, right? Between these, 9 different patches. And then you go to this, the normal like multi-head attention, normalization, MLP. Then finally, you have a class. If you're doing classification, then you have a classification token to aggregate the information and make the prediction. Okay, so this is very intuitive, right? Yes.
In VIT, is multi-head attention block used only once?
What attention?
The multi-head attention block.
No, you can have multiple of them, right? So you don't have to just using a single, block, attention block. You can actually using multiple of them, just like the original transformer. You can using multiple of them, yeah. But I think basically the difference is that, you divide the image into a sequence of patches and consider that as a sequence. Okay, so kind of similar, then the later can be similar as you process with the original transformer. Okay. Okay, so I don't think I have too much time, so I'll quickly skip this because this is all work. Another example, we try to using VIT for the human pose estimation. Again, this is just how we can using the VIT to deal with different data, right? So here, not just image, we are process a sequence of a pose, right? 2D pose, right? Or skeletons, right? So we can treat as each pose will be like a patch, if you think about original VIT, and we can process them, adding the precision encoding, and get a feature representation. So that's another example, okay? Okay, we can skip that. Finally, you may also heard of this cross attention, right? So, think if you're doing like a multimodal understanding, you may see papers. They also talk about like cross attention, right? So basically the same thing. Okay, the cross attention, self attention, the same thing. So the self attention, like QKV, they are coming from the same input, right? Like text or image. But for the cross attention, is basically, let's say you have a text input, but you also have an image input, right? So then you can, using the query that is coming from the text, but the key and the value matrix are actually from the image, right? So this is like a cross attention, right? So you are using the query from the text input, but you query the image branch, right? The stream, right? How this text is with the representation close to, or the similarity to the features in the image space, right? So that's the cross attention mechanism. So that will be used in like image captioning, vision language model, right? So here basically the equation here is that, right, you have a query text, then you have this K, which is using I image as the indicator, right? So then the value will also have I. But you can also work the other way around, right? So maybe the query is from image, but you also have the key and a value from the text, okay? So that's basically the same mechanism, but just using different key value and the query matrix from different modalities, okay? Okay, all right, so here I also provide some of the resource, right, the survey. If you're interested, you can look at these surveys, right? Different advancement or different architectures being used in vision in particularly, and also some of the, because this course we are dealing mostly with the images, right? So there's a lot of resources for visual transformer and also for medical imaging as well, okay? Okay, so I think that's all for today. Any questions? Okay, great. Okay, so yeah, this will be all for the deep learning. So hopefully, if you're not familiar with this, so this will give you some idea or the basic knowledge. And the next class will talk about medical image classification. Okay, all right, thank you. Yes.
First of all, so there is no mention of which optimizer should I use.